different operating points, because that point is not the same as that point. So. But in any case, they use this curve to show that, well, the optimal operating point for objectosphere is closer to correct, so it's closer to perfect classification. The perfect classification is here. You want false positive to be 0 and CCR to be 1. So that one is closer to there. Then using a background class, which is open max. So if you use open max, then you are very far. This is green, so this is entropic open set. So both of their methods are better than what they call the state of the art, which is background. So yeah. Okay, so even if you only pick one of them, you're better under the metric that they designed. Yeah, you got other methods like ensembles and so on, which we saw in the previous weeks. Okay.
What's the data set? Some color
MNIST. So they use MNIST for classification, and then they add another data set for the known unknowns. They add so they use different ones. So they use not MNIST, but they also use a different one.
There was something about target challenge. Was it?
About what?
About some target challenge.
The Vanguard data set. They also use this. I've never heard about this data set.
So can we just look at, if we go back to the ROC AUC graphs there that you just showed, please?
Yeah.
So if we're looking at the background set on C, on the open set classification rate curve, so we're looking at a false positive rate against the CCR.
Yeah.
But we are, you're correct in the assumption, right, that the entropic and the objectosphere perform higher. But then if we're balancing that on graph B, the precision versus the confidence, do we take that into account as well?
Well, what they, yeah. So this is actually interesting. So confidence threshold versus precision. So this is a different type of curve, right? Because this is just measuring precision, and then you start moving your threshold, and you see how the precision evolves with the threshold. And what this is showing is that at the limit they perform the same under this particular curve. Yeah, then they argue why this is not a good metric to measure the unknowns. We can go through them, but it's. I find it that it was just a list of why this is inconvenient for us and why this new is convenient for us. In any case,
So
I think.
So you disagree, or you just?
I do not disagree with the method. I think that the method is actually interesting, and it is achieving something. It is achieving an interesting separation between the unknowns and the known classes. I just criticize that they decide to say, yeah, well, we're going to use our own metric to assess our own method. Because it takes, so the metric deliberately takes advantage of the strong points of the algorithm, which the others didn't take into account. So I think it's a bit of an unfair comparison.
That's fair, but only if they also use the previous metrics. If they report all results.
So they report the results for the other metrics, showing that there is no difference. So if you see here, so using the precision confidence versus confidence threshold, they become the same at some point.
So it's fair, right?
The AUC, they are bringing AUC for...
The AUC, they do it for different algorithms, and they just show that it's completely irrelevant because algorithms with very different behaviors in the unknown set can have the exact same AUC curve. Whereas here they will have, if they have different behavior in the unknown, they will have different behavior here. But this does not measure when you got one of these in there.
I just wonder how do they decide like AUC for the unknown classes though?
Yeah,
They have a separate class of unknown. Yeah, so
so the AUC is putting, so you have, when you do AUC for the unknowns, you add one class
yeah, well,
that encompasses all the unknowns. So it is very biased towards the amount of classes that you are classifying and how many are in this set. So if this is very small compared to that other class becomes completely irrelevant. And then if this is very big compared to the number of targets that you have, then the metric also becomes irrelevant. It's very sensible to data set size.
Yeah.
Unless these two are comparable, or even better, this has to be comparable to one of the classes, so that the metric actually makes sense. And even then, you're just putting a whole bunch of unknown labels into one class. So it's not, yeah, that's the argument.
So I just want to draw out a little bit of what you're exactly saying just then. So that is basically, if your hypothesis is correct and that the arbitrary set of the metrics is relatively subjective, then how would you reduce the bias and increase the objectivity within the metrics if you could adapt that to something a little bit more fair?
So I don't know if I got the question right, but what they are trying to do here is to develop a fair metric. The criticism is not that this is a useless metric. It's just that it's a metric that measures what their algorithm takes advantage of, which is having low activations on the unknowns, so that you will have very few of these in here. So the false positive rate is going to be low because that is by proxy, that's what you're regularizing. And same in the correct classification rate, by proxy you're optimizing your softmax output in this set. So you're keeping all the benefits of normal machine learning, but then you're adding a regularization function that makes these activations be very low, so that you can threshold them. And indeed, with you can find a very good threshold for it. Yeah.
Just confirmation, because I would have thought, yes, as you said exactly, adding one class for all the unknowns and then doing the usual AUC would be all right, and why not take that? And you said the reason why you don't take it is because of the imbalance. If you have like the unknowns about the size of a regular class, we could actually do it. If it becomes out of proportion, then that's the justification of the metric. Is that correct?
Yeah.
Okay.
Yeah. Cool. Yeah. So the last result is quite simply showing the best values for each of the algorithms. So that's normal softmax performance, and background is open max. I assume that it's open max because they say they compare it with open max, but then they call it background. Open max defines a background class, but let's assume that's open max, and then there are two losses. And what they say is that the two losses significantly outperform everything. This scaled objective sphere is the softmax threshold times the feature activation. Okay. So yeah, they outperform with two different networks. So since it's a loss function, you can apply it to different architectures, which is a strong point for the paper, I would say. And the other strong point for the paper is that it's open source. So we can go to GitHub. It's in the first page. So GitHub, reducing network agnostaphobia, and all the code is there. So we can go ahead and try the algorithm. Yep.
The scaled objecto within the second architecture.
Yep.
What's the relevance or the function of that? Because obviously it performs high.
So it's the same.